Professor Louis Massa got his PhD at the Georgetown University in 1966, and then he went for a postdoc to Brookhaven National Laboratory. Since 1969, Professor Massa started working at the Hunter College of the City University of New York, and first as assistant professor, then associate professor, and since 1975, he is a full professor. Between 1970 and 1973, Professor Massa was the president of the Hunter College Senate. Since 1974 and up to 1975, he was the Hunter College ombudsman. And in 1980 up to 1981, he was the president of the Hunter College Faculty Union. Professor Mata got plenty different awards, including honoris causa doctorate of the St. Vincent University, ACS Westchester Distinguished Scientist Award 2019, Distinguished Visiting Professor at the United States Naval Research Laboratory, Keynote Quittel 2019 lecture, Montreal, Mathematical Problems in Quantum Crystallography and Their Solutions. Presently, he's the member, and he was in the past a consultant to the Commission on Quantum Crystallography of the International Union of Crystallography, and many, many others. Professor Massa got many different grants from the most prestigious American agencies, like NSF, NIH, IBM, NASA, Naval Research Lab, etc. And he also got numerous visiting professorships at such prestigious institutions like Harvard University, Brookhaven National Laboratory, U.S. Naval Research Laboratory in Washington, D.C., University at Bordeaux, France, or University of London, and many others.
Louis Massa is also on the editorial boards of the Structural Chemistry. He's also the Science and Technology editor of the City University of New York Television, and was the guest editor of the special issue Quantum Crystallography in Journal of the Computational Chemistry in 2018. He's the member of American Crystallographic Association, American Physical Society, American Chemical Society. Louis Massa presented numerous invited lectures at the very prestigious universities. Just let me name a few of them: Princeton, Harvard, Northwestern, Brookhaven National Lab, Naval Research Laboratory, University of London, Birkbeck College, ILL Grenoble, Weizmann Institute of Science, Rehovot, Uppsala, Beijing, and many, many others. Professor Massa is the author of 2 books, including Quantum Crystallography, jointly published in 2023 with Sheriff Mata, Lulu Huang, and Lulu Huang. And he's also the author of TV series and almost 250 published publications. He's one of the founders of the field of quantum crystallography, with numerous seminal contributions to the field, including the definition of the field of the quantum crystallography. So, Professor Massa, thank you very much that you have agreed to present this lecture, and the screen is yours.
Stuff. And Paulina, thank you very much for the invitation to speak and for the kind introduction. So you can tell from the title of my talk that I'm going to speak about the calculation of energy associated with a wave function of a particular kind called the kernel energy method wave function, which would be applicable in the case of very large molecules. And the topic of calculating energy, that's what I'm going to come to in the later part of the talk. But Christoph asked me to talk a bit about my early efforts in the field that has now come to be called quantum crystallography. And therefore, as you can see from this outline, I will begin by discussing the early work that we tried to carry out, and then I'll end with some actually very new material related to the kernel energy method that's applicable for large molecules. All of this is actually discussed in this very recent book that's been out for about a year. It's called Quantum Crystallography. It's a publication of De Gruyter, and all of the students that I have worked with are mentioned in this book. So I take a second here to thank the students for doing the work that made our contributions to quantum crystallography possible. So to begin with the work at Georgetown, together with Professor Bill Clinton, we were interested in the density matrix, whose definition you can see here. Of course, everything follows from the Schrödinger equation, in this case, the time-independent Schrödinger equation, which are the equations of motion of interest to us. And in this talk, the approximate solutions to that equation that I'll be emphasizing will be single determinant wave functions that are based on the product of molecular orbitals. But given the wave function, here's the definition of the density matrix. You see it's the square of the wave function integrated over all of the coordinates except the spatial coordinates of interest, which here are called r and r prime. That's the density matrix. I'm emphasizing that from the beginning right through to the end of our most recent contributions, our interest has been in the density matrix. Now, the reason I'm emphasizing that is that the X-ray scattering, which is the experimental basis, of course, for quantum crystallography, occurs from vibrations of the electron density. And there's a relationship, of course, between the density matrix and the electron density. The relationship is what you see here in this slide. That is to say, the electron density at a given position, R, is determined in terms of the diagonal elements of the electron density matrix, which is our principal interest. So if you set the coordinates R prime equal to R, then the density matrix resolves into the density. That's the relationship. We were concerned and have been concerned with the experimental measurement of the density matrix that you see here. If we go to the next slide, you see why we're interested in the density matrix versus the density. It's because using the ordinary rules of quantum mechanics, any operator can be obtained from the density matrix, according to the expression you see here. You know, usually the expectation values more commonly are written as an integral over a kind of sandwich integrand, psi star, the operator psi, integrated over all space and overall spin. But that, in terms of the density matrix, boils down to the expression you see here. The density matrix, of course, is simpler than the wave function. It retains all of the mathematical information required to calculate the expectation value. Now, in general, the density does not deliver the expectation value of operators that depend on, for example, the velocity or the momentum or the kinetic energy. For such operators, it's the density matrix that's required for the measurement expression, the expectation value. On the other hand, given any property, which is a function of distance alone, it's the density, of course, which when integrated in this product of the function of R times the density, it's that integral that gives the expectation value. So what I'm trying to point out here is that the density matrix is more general than the density. All operators have expectation values in terms of the density matrix. A subset of those operators, which are purely multiplicative in nature, such as functions of R, they can be obtained from the density alone. The density matrix, if that becomes the focus of your attention, you are immediately drawn into the problem of representability. And that's the relationship which guarantees a connection between the density matrix and a possible wave function from which it can devolve. So, for example, if you have a wave function, of course, you can integrate over all the coordinates and spins except for the spatial coordinates of one electron, and that integral will give you the density matrix. On the other hand, if you simply have a function of particle 1, it's not clear that there is a relationship which would send that object back into the wave function. N representability is the mathematical mapping which guarantees the relationship indicated by these arrows, that the arrows go in both directions. That is, of course, a wave function delivers a density matrix. But the question is, just given a function of position, defining a possible density matrix, does it go back to some possible wave function? And that's the problem of N representability, which is inherent in discussions of density matrices. So these are the unknowns, of course. It's the elements of the projector in this last slide. Let me go back to it if I can. You see, you can expand the density matrix in a basis of functions. Let's call them by the name psi. The weighting factors are the elements of the density matrix, and if that matrix is a projector, that's what guarantees the N representability of the density matrix. So in the next slide, what I'm trying to point out is these are the experimental unknowns in the density matrix. It's these matrix elements that can be fixed experimentally by fitting to X-ray scattering. And of course, one needs equations which will guarantee the N representability relationship. And these equations have been derived in this physical review paper at the bottom of the slide, but this is the form of the equations. These equations, called the Clinton equations, will deliver a projector, and they're solved very simply, actually. One just takes a guess at what the projector should be that satisfies the requirements that are represented by this matrix representative called O for the structure factors in the X-ray problem. This is the equation that guarantees the fit to the structure factors. The fact that this equation is satisfied is guaranteed by these Lagrangian multipliers, and the upshot of it is we get a density matrix in terms of a projector matrix P striking these orthogonal basis functions. That's been derived, and I won't go over the derivation, but of course one can reference this paper in physical review at the bottom of the slide for the derivation. So all of that was understood when I left Georgetown And as Paulina indicated, I went next to the Brookhaven National Laboratory, which is pictured here. And the thing that's interesting about my appointment at the Brookhaven National Laboratory, the thing that's interesting from the point of view of this lecture is that laboratory was a hotbed, one might say, for crystallography. It was literally filled with the personalities of leading figures in the field of crystallography. A few of the ones that I would have interacted with, I list here. And I went to Brookhaven National Laboratory specifically with the idea of getting support for the notion that the density matrix could be experimentally determined by measurements of X-ray scattering. So I'll just take a minute or two to say something about a small number of these crystallographers. This is a picture of Walter Hamilton, who was talked about by his peers as a genius. People actually applied that word to this guy. He was a student of Linus Pauling. He was involved with designing designing X-ray diffraction methodologies for the high flux beam reactor, both the design of the equipment and the software that drove the equipment. He's the driving force behind the protein data bank. And importantly, he was one of the supporters of the idea of trying to extract quantum mechanics from X-ray scattering. This is a picture on the right of, in the white sweater, of Ivan Bernal speaking to Wolfgang Schurer at a Sagamore conference in Halifax. And he's one of these giants from Brookhaven National Laboratory crystallography. He proved in the time I was there in a neutron experiment that neutrons alone could be used to solve crystal structures using direct methods. Sam LaPlaca is somebody I'll come back to. He was a great crystallographer, and he was important in the determination of the density matrix for the beryllium atom, which I'll come to in a moment. This is Philip Coppens, who is also present at Brookhaven in my time there. And one of the groundbreaking experiments he did with the high flux beam reactor is he calculated the electron density difference map, which is actually located next to his image here in the slide, which showed, of course, that non-spherical elements of the density could be, in fact, measured. And this is Roger Lalansat, who's presently at Rutgers University. We're still in touch. I'm still in touch with Ivan Bernal. We talk about once a week on the average. So all of these people have been a great influence. Now, when I left Brookhaven, Clinton and I wrote a paper which emphasized the difference between what could be done with the electron density matrix as against the density. And I'm not going to go through the details of the paper, but I'll just reference it here at the bottom of this slide. It's a Physical Review Letters paper. And in this paper, which is quoted here directly, we make the point that the least squares fitting to the X-ray scattering will drive the result towards the best possible density, but in fact away from the best possible density matrix in the sense of capturing the n representability, which is a quantum mechanical requirement for the electron density matrix. Now, a good number of those names that I interacted with at Brookhaven, we all left Brookhaven at roughly the same time, and that included Sam LaPlaca. He went to the IBM Watson Laboratory in Yorktown Heights, and he was the in-house crystallographer there. And we kept in touch. He invited me there on a sabbatical, and I spent a year in this building working with Sam. And in particular, we used X-ray scattering data to determine the density matrix of the beryllium atom, the structure of which is represented here. And what we found was a density matrix which captured the essence of the structure factors with real accuracy, as represented in this graph of delta F, the errors in the structure factors, which are completely random over the whole range of angle scattering, which was quite a remarkable result at that time and contrasted with other attempts at obtaining the same kind of information. I should mention in passing that the data that we used in this particular calculation was that due to Larson and Hansen. And I wrote a paper in the journal, in a structural chemistry journal, that indicated how this most important, most accurate data fell into our hands and resulted in the representation in this particular slide. So, in summary, structure factors, as indicated by the symbol F of K, K being the direction of scattering, these structure factors can be represented in terms of a projector matrix, which is, of course, defined by this square of that matrix equaling the matrix itself. And of course, it has to be normalized properly to account for the correct number of electrons. But such a projector, in fact, delivers the structure factors, in which case the density matrix written in terms of that projector upon a basis of functions, that is guaranteed to deliver the quantum mechanical n representability, which is a requirement of representing electrons which are identical particles. Identical in the sense that a switch of any pair of such particles has to leave the physical system invariant. That's the importance of n representability. Maybe I should emphasize that. The whole point of n representability is that electrons, the objects which scatter, in fact, are physically indistinguishable. That means, of course, that an interchange of any pair of electrons leaves the physical system invariant. So given that experimental fact, if quantum mechanics is to be correct, there has to be a mathematical representation of that indistinguishability. And that is the point of n representability. It's the guarantee of the theoretical expression of that indistinguishability. A bit later, actually in 1985, if my memory is correct, I began to work with Jerome and Isabella Carl, the famous crystallographers at the Naval Research Lab in Washington, D.C. And a shift of interest occurred at the Naval Research Lab for us. And the shift had to do with how are we going to represent the case of very large molecules that might have not just thousands of atoms, but tens of thousands or even greater numbers of atoms. And that's an interesting problem because the number of elements in the density matrix, of course, grows very big as the square of n, the number of atoms. And that growth in the number of experimental parameters at some point is going to outweigh the number of scattering factors which are measurable and which are used to determine those matrix elements. So the question arises, how are you going to treat the scattering in such a case? In our resolution of that problem, which occurred at the Naval Research Lab, was to use the multiple expressions of the electron densities to determine what I might call the classical crystallography. That is to say, use multiples to determine the atomic structure, the position of the atoms. And then given those positions, simply calculate with the methods of quantum crystallography. Sorry, I said that incorrectly. Simply calculate using the methods of quantum chemistry, the everyday methods of calculating wave functions. We simply use that in connection with the known atomic structures that would result from multiple representation. So that was the line of reasoning that came up at the Naval Research Lab. And in exactly that era, Jerome Karl was awarded the Nobel Prize, as is indicated here. And I wrote a paper for the American Chemical Society, who asked me to write about this. In fact, I wrote a paper indicating that it was a bit not understandable as to why Isabella Karl would not have shared in the Nobel Prize, because it was her experimental work that showed the mathematical results of Karl and Hauptmann. In fact, their direct methods, in fact, would lead to crystal structures. In any event, she she was a great scientist, and she was awarded the National Medal of Science by these heads of state that you see here. One thing that's kind of mildly amusing is Professor Bill Clinton one day tried to get me on the telephone at Hunter when I was not in my office. So he called the department secretaries and asked if they would track me down. And when they came to me, they were totally excited and said, "Lou, Bill Clinton in Washington is trying to get you on the telephone." And of course, it was not the person whose image you see here. It was the more important professor of chemistry and physics from Georgetown University. But in any event, to get back to the point of work at the Naval Research Lab, we were interested in the question of the density matrix for very large molecules. And to get at the solution to that problem, we had to invent a new method of getting at the density matrix. And we decided to simply calculate it based on known structures that would come from multiple representations of the density. And my former student, Lulu Huang, who was a senior scientist at the Naval Research Lab working with Jerome Karl at the time, she's largely responsible for the success of the venture of creating the kernel energy method, which I will indicate to you in a few words here. The idea is incredibly simple. Suppose you have some molecule, such as the one that's represented in stick figures here on the left-hand side of the slide. The idea of the kernel energy method is simply to take a big molecule of whatever size and cut it into smaller molecules. The advantage of which is that the smaller molecules can individually be calculated, and then they can be put back together according to a kernel energy method description that I'll show you in a minute. But this is accurate and fast, and we've published, I don't know, 20 or 30 papers, which are severe tests of the accuracy. And it turns out that the ab initio quality of the density matrix is preserved in this kernel energy method process of cutting big molecules up into small pieces, recalculating them, and then putting them back together, accounting for their interactions. And in this slide, what I'm trying to emphasize is that every one of these fragments, which in our method are called kernels, every one of them can be sent to an individual computer processor, and they can all be calculated in parallel, which of course speeds up the computation dramatically. Here's the basic idea, and it's consistent exactly with quantum mechanics. This is not an arbitrary summation of the energy. It's in line with the exact meaning of the energy of a group of fragments. So the total energy on the left-hand side of this equation, you'll notice, is written on the right-hand side as the sum of the energy of the individual fragments. But then appended to that is a sum of all of the pairwise interactions. And it's these pairwise interactions which account for the real accuracy of the methodology. Now, of course, in a system, you would have not only pairwise interactions, but you'd have triplets and quadruples and so on. And we've looked into all of that. And indeed, by taking into account fragment groups of ever increasing size, you can make the error of this energy as small as you wish. But what we found was that chemistry could be represented perfectly well by going as far as the interactions of the pairs, which we call doubles. So if you take these interactions into account, and they're defined here, you see, in any particular double kernel, you calculate the energy of the double kernel and reduce it by the energy, which is the sum of the pieces that make the double kernel up. That gives you the interaction energy in this summation. And in the next slide, I think I can show you the working form of the kernel energy method. It's the statement that in a physical system, which has been broken into fragments, the total energy is the sum of the energy of all the double kernels reduced by the sum of all of the single kernels. It turns out, the upshot of that, it turns out that that method works amazingly well. It retains the accuracy, the speed of the process. But we are interested in representability, you will recall. And the question is, what about the n representability when you've taken a molecule or a physical system and you've broken it up into pieces and then tried to put the pieces all back together, accounting for their interaction between and among those pieces? What about the n representability? Well, it turns out you have to impose that n representability again in a mathematical way. So my student Walter Polkoznik, whose name, his Polish name is indicated in the bottom of this slide here, Walter Polkoznik took this problem under wing and showed, number one, the kernel energy method is not n-representable, and then he showed how you could make it n-representable. So we did it with this set of water clusters. And I'll skip to the results here in order to save time and indicate that if you simply calculate the energy of a set of water clusters, which are listed here along the left-hand side as 10 in number down to 20 in number, it turns out that some of these clusters, as indicated by these negative signs and this difference of the kernel energy method energy as against the full molecule energy, the negative sign indicates that they're defying the variational principle, They're giving energies that are below the exact values. But on the other hand, Walter showed that if you use the Clinton equations to turn the kernel energy method density matrix into a projector, all of these negative signs, when you calculate the energy difference, they all disappear. They're all restored to N representability, and in fact, the accuracy is increased as well. So, given that result, that we can make the kernel energy method N representable, how do you calculate the energy using those kernel energy method results? Of course, the answer is here. The total energy is the sum of two pieces, one of which depends on the one particle part of the system Hamiltonian, and the other of which depends upon the two particle part of the system Hamiltonian. And for each of these, you need either the one particle density matrix, which has been the focus of our attention, or the two particle density matrix. But if you know the N representable one particle single determinant density matrix, rho 2 is a known functional of rho 1, and I'll show you that known functional. Here it is. It's the statement that the two particle density matrix in determinantal form is this little 2x2 matrix of the known kernel energy method one particle density matrices. It's the determinant of that. So if you know rho 1, that determines through this functional relationship rho 2. So the question becomes, if rho 1 is this summation of two parts, a double kernel part and a single kernel part, what's the algebra associated with this evaluation of this functional that will give rise to the two particle density matrix? Well, we have worked that out, which I will show you. We have worked that out, and it comes down to this. Here's the expectation value of the one particle Hamiltonian, and here's the expectation value of the two particle Hamiltonian. And the point of this is it's a vast simplification of using the full n particle wave function for expectation values. The most complicated calculation in this expression would be for a double kernel, which could be orders of magnitude simpler than using a density matrix for the full molecule. So that's the main result in terms of the energy calculation using this fragment method that we invented. Now, something very recent is the realization of what is the physical interpretation of this two projector triple product. So let me talk about that for just a minute or two. Suppose, for example, you have a projector P, which describes the electron density for a full molecule. And suppose further, by means of the kernel energy method, you have a fragment projector P prime, which is in a subgroup of the full projector P. This triple product here, P prime, P prime, this two projector triple product has, it turns out, a well-defined physical interpretation. And that is that this product delivers the projection of the full molecule onto one of its subspaces as represented by the matrix P. You can convince yourself of that by playing with elementary examples like this. Suppose you have a little 3x3 matrix and these X's are not, they are just placeholders. And suppose you have this projector which represents some full molecule. And suppose further, by means of kernel energy method calculations, you have these subgroup projectors P prime. Just by playing with these matrices in ordinary matrix multiplication, you can convince yourself that the triple product reduces the projection of the full molecule into a subspace of that full molecule. And what that means is, in terms of, given that physical interpretation, what that means is that a full molecule can be decomposed into such triple products in exactly the kernel energy method form. And this is an unpublished result. It's an exact decomposition of a full molecule projector into its kernel double and single fragments, plus the cross terms among all of them. And this paper here in the International Journal of Quantum Chemistry is a discussion of the use of these triple products. But the exact equation that is written, in fact, is so far unpublished. The cross terms are a bit of a nuisance to deal with, but they can be removed by a process of Gram-Schmidt orthogonalization of the triple products. That is to say, each of these triple products, by orthogonalization procedures, by this name, can be turned into a set of matrices of exactly the same size, but having the property of being orthogonal to one another, as indicated here, in which case the kernel energy method reduces to its simplest form that you see here. So that concludes what I want to say about the calculation of energy by this methodology called the kernel energy method that was invented at the Naval Research Lab. Everything that I've discussed is contained in this fairly new book called Quantum Crystallography by De Gruyter, publisher. And on the left is a picture of the two co-authors of this book, Sharif Mata and Lulu Huang, my former PhD student and a colleague of Jerome Carl, of both Jerome and Isabella. And there were contributions to the book by the Nobel laureate Adi Onath, who wrote the beginning notice in the book, and remarks at the end of the book by the quite famous philosopher of science, Olympia Lombardi. So I recommend this book to you to further find information about the kernel energy method and in general, what our contributions to quantum crystallography might have been. And quite a famous scientist, whose picture I will try to show, Istvan Hargitai, wrote a very scholarly review of this book, and I recommend that review to you in structural chemistry. And my final word is to point out that in 2017, as I recall, there was an explosion in the interest of the field, quantum crystallography. And that occurred at a little meeting. There were only about 20 people at this meeting in Nancy in France. And the names of all these people actually are listed below this picture, which occurred in the European Journal of Chemistry. And all of these names are the names of that go with the images that you see here collected in Nancy. At this meeting, this very small meeting that, as I recall, it lasted for a couple of days. There were intensive talks about the nature of quantum crystallography. What is it and what should it become? And out of that meeting arose a paper that was written by all of these people, in fact, each of them giving a sense of where they think quantum crystallography might move in the future. And for my portion of the paper, wrote about the kernel energy method, but everyone wrote about different aspects of quantum crystallography. And if one is to try to grasp the present nature of the field, the reading of this paper that is written by all of these people that attended that meeting in Nancy, that would be a really good place to start. I will end there by thanking Christoph and Paulina again for the invitation and thank you for attending this conference. If there happens to be a question, I could try to speak to it. Thank you.
Thank you very much for excellent lecture. And now we are open for questions, comments. So please put your questions to the chat.
Before the first question appears, in my opinion, quantum crystallography now is really blooming, and we can see a big increase of papers, and the whole community is maybe at least 100 people, maybe even a little bit more than 100 people all over the world, and the lectures at different conferences. I mean, the lecture halls are full of participants interested in topics. So it's really very nice to see this, and in fact, this is for me a kind of a revolution in crystallography. I mean, so plenty of different fields of crystallography could be improved with this quantum crystallographic approaches. That is really absolutely fantastic. So one big thank to you, to other people who really started this field, because without this beginning, we wouldn't be observing this big interest now.
Yes, I think the field has really exploded after the meeting in 2017 at Nancy. It was such an interesting idea that that meeting was put together, and so much has evolved from it, including the creation of the permanent study section of quantum crystallography under the rubric of the International Union, which of course is sponsoring this series of talks that we're in at this very moment.
And the beauty is that it's many things to come. For example, the method you propose, the kernel method, and including a way how to keep this and representability still for the kernel method. As I understand, it's still at the form of equations and examples of calculations, but was it already applied to analyze some experimental data? Do you have some examples of application of the method to some experimental data, or it's still at the level of being developed from the probably software point of view, I guess?
Yeah. Well, at the outset, we had a whole series of very small examples that started with theoretical data. But the breakthrough for us had to do with the beryllium crystal. I was at a small meeting in New England. It was called the Gordon Conference. I just remembered. And there were people from all over the Western world at the conference. And one of them was Larson of Larson and Hansen. And Sam LaPlaca and I were talking about beryllium. And I wrote a paper called The Pathway, a Zigzag Pathway Through Quantum Crystallography, in which I discussed how we came upon the most accurate diffraction data of the time due to Larson and Hansen. And it was simply because Larson was at the meeting, and without talking to me about it, he simply said, if you're interested in beryllium, you should look at this. And he handed me a little green booklet with the most accurate data possible. And Sam LaPlaca, who is a great crystallographer, looked at this and realized this was a gold mine of information. And it was with that data that we solved for the density matrix of the beryllium atom. And the density for the beryllium atom had been calculated theoretically by Cohen at Berkeley and by Dovesi in Italy. And when we compared our results to their quantum mechanically purely theoretical results, the comparison was right on the button. And it's in our physical review letter that we published in 1985. So that was, to get back to your question about are there experimental results? The beryllium crystal case with data from Larson and Hansen, that was the breakthrough case which showed you could extract from the X-ray scattering data the quantum mechanics as it resides in the density matrix, which in fact is n-representable. The reason I started my lecture with a slide, the very first slide had the definition of the density matrix on the one hand, as against the density on the other hand. The reason I started with that is there is a tension that I perceived between the crystallographers, the crystallographers who own the field, basically. They're the ones who are taking the experiments. There's a tension between trying to get the density that does that scattering on the one hand, between them and the theoreticians who are trying to extract from exactly the same data the density matrix. And that tension from the very beginning still exists right up until today. And it's very interesting to recognize that tension.
Yes, I fully agree. So that was the very first experiment, but I was wondering whether you had chance to apply your kernel method for bigger molecules to some experimental data of
The
bigger molecules with kernel. Yeah.
Yeah, the kernel energy method. We have not been able to apply that as yet with experimental data. And the last slide that had to do with these triple products, that's actually unpublished material. So certainly that has not been applied yet. But to get back to the point of your question, the answer is we have not applied that method with experimental data. But what we have done is we've published 20 or 30 papers, Jerome and Lou and Sharif, the group of us, we published 20 or 30 papers checking the accuracy of the kernel energy method and the speed of the method against others. And what we have found is, the point of all that is we have proved that this method could be applied using the Born-Oppenheimer idea that if you know where the nuclei are, as for example, given by multiple representations of the density, then you can simply use those nuclear coordinates in connection with the kernel energy method to get the correct density matrix and therefore the correct quantum properties of the system. But the simple answer to your question is it remains to be done to bring in the use of experimental data.
Yes, we have a question from Julian Hen. Can your kernel energy formalism be extended into a form that includes gradients for the geometry and used for geometry optimization?
So I think it is about whether you can apply kernel energy approach in geometry optimization procedure.
That's a great question, by the way. And the answer is yes, but we have not done it. But that is a really great question, and that's something that should be done. That is to optimize the that's what they're asking about. Thank you. They're asking apparently about, can you optimize the geometry using that method? And the answer is yes, but it hasn't been done. So there's a paper that somebody could work on, for sure.
And there's a comment from Jean-Michel Gillet. Nice talk, Lou. Thank you. Thanks. I have to run. Sorry.
Except this direction towards macromolecules, what other big applications do you foresee for quantum crystallography? In your opinion, what are the other important directions in which quantum crystallography could somehow be developed?
Well, the main object of this talk was to write down the kernel energy method expression, which would give one the ability to calculate the energy of a large molecular system based on knowledge of the crystal structure associated with, say, a multiple representation of the density. So that's the idea. So then the obvious sort of applications in my mind would be single crystal data associated with large biological systems. DNA, RNA, a calculation that we actually did with Adiyanath was related to the ribosome. You know, Adiyanath's group had the idea that the modern ribosome, which is of course a gigantic system, has an evolutionary precursor that they call the I think they call it the I forget the exact name, unhappily, but I think it was called a proto-ribosome. Mm-hmm. So the question is, that evolutionary precursor, which is really small, having, you know, tens of thousands of atoms, but not more than that. Given the structure that exists today in the present ribosome, can you pluck that evolutionary precursor out of it? Uh-huh. And if you do, will those atoms create a peptide bond? You see. So we were able actually to use the kernel energy method. Maybe this gets back to a previous question about experimental data. We were actually able to use the experimental data of the present day ribosome, extracting that little piece called the proto-ribosome. It's little, but it had tens of thousands of atoms in it. And we were able to show that it has the capacity to create the peptide, to hold together the pieces that would create the peptide bond. Now, we were able to do that because the kernel energy method is adaptable. Now, but to get more directly to your question, take the case, you know, the general answer to your question is, I think large biological molecular systems is the place where the kernel energy method would be applicable. And a specific area along those lines is the case of drug design. because drug design very often amounts to the question of how does a small molecule interact with some big biological system? So that interaction depends on the course of the energy as the drug approaches the target. And that energy and the difference of energies, the delta E's associated with the drug interaction, that actually can be calculated using the kernel energy method. And we wrote a paper, of course, arguing that case related to drug design.
Yeah, that is a really great application.
Bisfait Mohanty is asking, how can the basis set superposition error, BSCCE, be minimized when using kernel energy method for biological systems in an implicit solvent environment? So we have a question about superposition error, basis set superposition error, and using implicit solvent in the calculations.
Well, in terms of solvent, we did a calculation on insulin, about 1,000 atoms. And there were solvent molecules in the crystal structure, and we simply took them into account as additional parts of the fragment. In other words, the solvent molecules, if you know them from a crystal structure, they're simply part of the calculation. They contribute to the fragments. But you also asked about the superposition errors associated with the basis. I haven't ventured into that, so I can't speak to it. But I'm certain we can take care of it. There are methods. Other people have worked on methods, have they not, to account for basis set superposition? So we could take that into account, but we have not. One thing I would say is I think quantum crystallography is just at the very beginning of its development. I think really big things will happen because there are so many talented people, as in that picture in my last slide, for example. There are so many talented people in the field doing things that I can't help but think that great progress will be made.
Yeah, that is actually excellent closing of our seminar. Thank you very much, Lou, for your beautiful lecture and also for this discussion.